Hello, everyone. Nice to meet you in Atlanta. I will introduce how to streamline LLM fine-tuning on Kubernetes with Kubeflow LLM Trainer. But before the talk begin, please let me to introduce the speakers today. Andrey serves as a member of Kubeflow steering committee. Regretfully, Andrey cannot talk in this session due to some internal reasons in his organization. But I want to express my sincere appreciation to his great contribution to these slides and to this talk. My name is Shao Wang, a second-year graduate student at Shanghai Jiao Tong University, and I'm also a member and I'm also a maintainer of Kubeflow Trainer, Khatib, and SDK. Let's start our talk today. First, I'll introduce what is fine-tuning. Fine-tuning is a procedure that you adapt your base model to specific application scenarios using domain-specific datasets. After that, your model will have a stronger ability in that area and can answer some complex and domain-specific questions. Like the example we show in these slides. You ask, what should I do when I catch a code, for example. After the fine-tuning, before the fine-tuning, the base model may answer no ideas. But if the model are fine-tuned with the domain-specific datasets, like medical datasets, they can give more professional advice, like drink some water. That is fine-tuning. The process I show sounds really easy, right? But in reality, it's not as straightforward as I described, especially on Kubernetes. It typically involves an endless loop of write ML code and the scale and fine-tune model on the Kubernetes. The loop is ended only when the model quality can meet some criteria, like reach some scores on the benchmark. Now, do you think that's all? No. The bad news is that there are more difficulties in practice. In order to fine-tune LLMs on Kubernetes, you need to configure various settings besides writing the ML code, like configuring Docker images, setting up distributed environment, downloading models, and exporting artifacts. And what makes things worse is that you might need to reset these configurations every time you rewrite your ML code. So a lot of time might be wasted to tune these configurations, and that makes the development process inefficient and painful. That's a pain point for data scientists. However, data scientists that fine-tune the LLMs do not want to touch any of these complex Kubernetes configurations. They just want to quickly iterate their ideas while leveraging the ability of Kubernetes, like scalability. Their core requirements are simple to use, flexible to change, and scalable to chain. So the first demand from data science is simple to use. Let's see what is unsimple or difficult for the data scientists. As data scientists, they know how to use the PyTorch API to build models and fine-tune models. However, they are not familiar with Kubernetes as well as its configuration, right? No one likes to see so much YAML files, even if they are expert. We can recall that how depressed and painful we are when we first met Kubernetes and its configurations, right? It's just the same feeling that data scientists are experiencing. However, the fact is that these configurations are necessary. They are crucial in keeping the fine-tuning jobs running in the desired manners. So the challenge for us is how to hide these configurations for data scientists and make sure fine-tuning jobs run in the desired manners. To solve this challenge, our key solution is to design CRDs for different personas. Please look at the middle of the graph. The training runtime CRD is managed by DevOps engineers using kubectl. Training runtime CRD is a blueprint. You can understand it as a blueprint for fine-tuning jobs. It contains all of the default configurations to fine-tune an LLM. Most importantly, it includes nearly all of the Kubernetes configurations and is managed by DevOps engineers. Now, please look at the top part of this graph. You can notice that train job is managed by data scientists using the Python SDK. Train job is designed to override and mutate the settings defined in the training runtime, like GPUs allocated to each fine-tuning node, training image, and number of nodes. Then our controller you see in the bottom part of this graph. The controller will create fine-tuning jobs with job set CRDs according to the mutated configurations. And please let me use an example to show, to have a better understanding of the relationship between training runtime and training job. On the left is it's a training runtime created by DevOps engineers. It contains all of the necessary configurations to start fine-tuning jobs, like images and start command and the resources and other necessary configurations. On the right is the training job CRD. It only consists of the necessary overriding configurations that allow data scientists to customize their fine-tuning jobs. For example, from the top to the bottom, the runtime ref field means that this train job will use the reference train jobs, or in other words, this train job will override the configurations in the left training runtime. And next is a trainer image. It means that the data scientist will use these customized images to replace the default image in the training runtime. In the bottom, the resources per node set in the train job is to override the per node resource configurations defined in the training runtime. In this way, data scientists can get rid of the complex Kubernetes configurations and only concentrate on the parameters that are highly related to fine-tuning. So we make this process easy. Now we've solved the first challenge and make fine-tuning on Kubernetes simple. The next requirement is flexible to change. What is flexible to change? I think it means that the data scientists can quickly iterate their ideas. So we first define what is unflexible. The fact is that every time data scientists change their train script, base models, and data sets, they need to configure and change the YAML file. Look at the workflow below. When user changes the train scripts, typically they need to rebuild the image, push it to the image registry, and configure the new image in the YAML file. And another case is that when data scientists decide to change their base model and training data sets, they need to download it from the remote, load it to PVCs, and configure PVCs in the YAML file. It's manual actions waste a lot of time and hinder data scientists from quickly iterating their ideas. However, these actions are also necessary. Then the challenge is how to avoid reconfiguration every time the following items change, like fine-tuning techniques, full fine-tuning, LoRa, knowledge distillation, and even RL, and distributed strategies, DP, TP, and as models as well as datasets. Changing any of them needs to reconfiguration. To solve this challenge, we propose built-in trainer, also known as a Torch2 LLM trainer. The first highlight is it streamlines models and dataset downloading, fine-tuning, and artifacts exporting in a single workflow without individual involvement. The second highlight is we provide a simple yet efficient Python SDK for data scientists to manage this workflow. Let's see the first highlight. In the streamlined workflow, before launching fine-tuning jobs, you can see from the top of this photo, the storage initializer in the top will first try to download models and data sets from the remote. When both model and data sets are available, the fine-tuning job starts. Then the model exporter will export the model to cloud storage like S3 after fine-tuning finishes, or just leave them in the PVC. This process is automatic and does not need data scientists to manually set up all of these steps. And we also provide, we made this workflow editable. If the data scientists just want to use the default base model data set and fine-tuning strategies and distributed strategies, they can just do not change anything and just fine-tune the model with one line of code. The picture shows just like this. And next, data scientists can customize this workflow if they do not want to use the default settings. Like the example shows, user can smoothly change the base model and the data sets. And you can see use the fine-tuning techniques. Use a lot of fine-tuning if they do not want to fully fine-tune the model and assign GPUs to each training node. This design makes fine-tuning on Kubernetes flexible and scalable. So to sum up, Kubeflow LLM Trainer has made fine-tuning on Kubeflow easy to use, flexible to change, and scalable to train. Let's watch a demo to have a better understanding of Kubeflow LLM Trainer. Yeah, let me. First, we will list the training runtime available, and we can show that we can see the LLM Trainer supports Llama 3.2 family and Q1 2.5. And if users do not want to change the default workflow, they can just start this default workflow with just one line of code. And we can wait for the job to run. Just waiting. Yeah, OK. And we can see that the dataset initializer and model initializer has downloaded the model and the datasets, and the fine-tuning jobs are running. And you can check the logs. Datasets, model are all downloaded to the PVC. And we'll see the training node log. And we can see that we use the instruct dataset to fine-tune the models. And we use Llama 3.2 and tokenizer. The model is still loading. And we are pre-processing the datasets. Generate train script split. And now the fine-tuning starts and ends. But if you do not want to use the default workflow, you can customize this workflow with your own settings. Now you can use change the model to Q1 2.5 and and specify the data process configs and the data sets, and allocates 35 GB memory to each node and 2 GB to each node, and use the longer fine-tuning if you do not want to use the full fine-tuning. Yeah. Similarly, you can see that there are two train jobs in the logs. The first one is the current one, and the previous one is complete. In practice, you can start these two jobs concurrently and this will allow data scientists to quickly iterate on their ideas with the help of Kubeflow SDK, as Tony and Anya showed before. And we can see the training job logs. Simply use the instruct dataset. Use the Q1 2.5 and enable the LoRa configuration. And the model is output to the directory. This is the configs generated by the torch-tune. And we can see that it's the same as we see in the change of logs. And the fine-tuning has ended. And the LoRa adapter has been exported to output/output directory. And in the end, we can get fine-tuned models and start the serving. We load the base model from output/model and load the LoRa adapters from the output/output epoch 0 and start explain shortly what is Kubeflow Trainer, and the model generally responds that Kubeflow Trainer is a framework that simplifies the process of training machine learning models. Yeah. I think that's all. Yeah, let me share my screen. Yeah. Up to now, we support Llama 3.2 model family and Qwen 2.5, and we will support more models in the future. The next step of Kubeflow LLM Trainer is to support dynamic LLM Trainer framework. As shown in the graph, we will implement a unified Python API to allow users quickly changing between different fine-tuning backends. For different framework users, this design can make the fine-tuning LLMs on Kubernetes simpler and more flexible. And we will support Sloth, Llama Factory, TouchForge, and more popular frameworks in the future. And we are sure that this will streamline LLM fine-tuning on Kubernetes and accelerate innovation. If you are interested in joining us, you can join our CNCF Slack channel to discuss your idea with us, or you can attend the bi-weekly meeting of Kubeflow Training and AutoM working group. You can scan the QR code to learn more if you want. And in the end, thank you for listening.